Solid-state electronics. This is one of our chapters that we had to do for this project. This was chapter 19 in our book. The other one was nuclear applications, which was chapter 21. At the most basic level, solid-state electronics is an electrical device which is non-moving parts, most commonly in modern day, the microchip. How do they work? Circuitry that is built into the board controls the flow of electrons in order to process and translate and compute data. Today they are used in everything from thermostats to desktop computers to car radios. You probably couldn't look in many places that wouldn't have some kind of circuit board behind it. Conductors. Conductors create a pathway for electrons, moving them along through or the correct component that their specific type of data is for. Most metals can be used as conductors, but some are far better than others, like silicon. Conductivity is based on the energy spent while traveling through the object. It's pretty simple. Conductivity is similar to other things. Insulators. Insulators do the opposite of conductors. They prevent electrons from escaping or passing through them. They may not be the main focus of the show, but they maintain an important role in both safety of the parts and preventing electrons seeping. They also create the structure in which circuit boards are built on. Imagine how this unsoldered circuit board functions much like the image of the rubber coating on the circuit. It both houses and protects the pieces. Without it, the components carrying the electrons would act much like the third picture, passing electricity with no boundaries, wasting electricity and skipping important pathways. Being very dangerous. It's almost unfiltered electricity, I guess.
I mean, the data wouldn't go on.
Yeah, or the data wouldn't go along properly. The transistor. A transistor is the most basic component behind a current solid-state electronic. It is used to amplify and switch direct signals in a device. Every year they become smaller and more efficient, as pictured. The history behind the transistor was one of the first, I guess, key components in modern-day electronics. The first solid-state components were compressed conductive gas into glass tubes known as vacuum tubes, which are those big tubes that you see on the old TVs, and they're in like 80s computers that are huge.
The wall-sized computers. There were a lot of moving parts within the computers, but the first solid-state component that made up an electronic device was the vacuum tube, and the transistor was actually its replacement.
Okay, so the transistor came after the vacuum tube,
Yes.
which functioned in extremely large first computers. Now with Moore's law, which we'll get into later, ever looming over our heads, they may be the next step in solid-state electronics, being that nano vacuum tubes could provide a possible alternative to silicon chips. There's Moore's law. Modern solid-state electronics use transistors, which are comprised of silicon, an extremely efficient metal. Every year, transistors become more powerful and smaller in size. Moore's law states that this exponential curve has a limit, stating that eventually we will not be able to further manipulate silicon, all but halting advancements in computers and electronics in general. The reason that this is so intimidating is that it's so integral, it could be enough to crash the world's economy. No iPhone 8, no new hardware. The only improvements we could make are those based in software. So there's a limit to our...
The malleability of silicon.
Yes, so the prospects of silicons are limited. And this is band theory. It's a very complex theory which would take a lot of explaining. I'm going to have Zach come over here and help explain it a little better.
Basically, the bands function like pathways for electricity. The more bands that there are, the more pathways there are for electricity to follow through. So it operates in solid-state electronics as kind of a data highway, you could call it. So the more bands there are, the more conductive an object would be. So this would be something like silicon, and this would be something like rubber.
So it's basically a ranking system for the conductivity of silicon and rubber and just conductors. In modern day, most of your smartphones, tablets, and even some laptops now function off of solid-state electronics, being that they consume less electricity and can be far more compact. So
They're also, they resist more damage. So if you drop the desktop computer, the moving parts would break it most likely. But if you drop something like a smartphone, it would easily survive.
So it's all around better. Yeah. And this is nuclear applications, which is chapter 21. And this is
Nuclear applications could easily be one of the most dangerous and controversial areas of science, encompassing nuclear power, nuclear bombs, radiation therapy, and anything else involving nuclear energy being utilized by humans. Radioactivity implies that a material is unstable at its base level. It produces energy or radiation from within its nucleus in order to shift to a more stable state. The details of why this happens are fairly complicated, so I'll just do my best to kind of mull over the meaningless details. The process is begun by having too many neutrons within the nucleus, which then causes it to emit energy. Telling a neutron to become a proton. However, this continues to happen, and too many protons accumulate, which leads to the nucleus producing a positive electron, changing the protons back into neutrons. This could be comparable to something like a dog chasing its tail, or any other vicious cycle you would think of. As this process continues to happen, energy builds up and gamma rays are then released, displacing a large amount of energy, however, leaving the nucleus the same. However, if the mass is too great in something like uranium or plutonium, which is one of the more unstable ones, something called an alpha particle is released, and the nucleus is told to drop 2 protons and 2 neutrons, which reduces its mass and makes it more stable. As this process goes on, energy is created and used, and then it decays. In the medical world, one of the longest radioactive applications in the medical world has been radioactive imaging, either in X-rays or radioactive dyes. Mostly iodine is used. In order to aid imaging by isolating specific structures, mostly iodine, in order to aid imaging by isolating specific structures in the body. As well as imaging to find flaws in structures, sometimes radiation is used to shrink things like dangerously large tumors, atrophying them much like unencumbered radiation atrophies all life forms. Nuclear power. Nuclear power holds the greatest promise and risk at the same time for supplying the world with sustainable energy. It uses power created by radioactivity to heat pressurized water in order to turn a turbine, which is connected to an alternator, which generates electricity. This water is then cooled and released out of a cooling tower. Now, mind you, this is the simplest level. A reactor is a very complex structure to maintain. It must always be supplied with a fresh amount of cool water to prevent the always imminent meltdown, which would cause the double threat damage of both the heat it releases, would be immense, and the irradiated landscape and life, which would kill pretty much all life. Next. Risks. Delving more into the risks, nuclear energy, although promising, has some very severe risks, either to the health of those who simply come into contact with too much radiation, or the widespread destruction of a failing reactor. Pictured is the Fukushima power plant that we all know about, I'm sure. Due to this fear, many Americans are fairly uneasy about nuclear energy. Even provided with the promise it can garner. Okay. Funding. Being that nuclear power plants, at bare minimum, run hundreds of millions of dollars, more often than not, tens of billions of dollars. Not many companies have the resources to create power plants. So the government funds most of the power plants, like other governments. So pretty much if you see a nuclear power plant, it's most likely owned by the government and run by a private company. That's it. That's 9 minutes and 30 seconds.
Plus credits.
Oh.